Your lab experience so far with redox reactions is with using the activity series to identify single displacement reactions. We use the activity series to decide when a metal will react with water, when it will react with an acid, or when one metal will displace the electrons in another. So for example, if I have a container of copper nitrate or sulfate solution and I put a zinc bar into that solution, what's going to happen is a redox reaction. The copper ions will gain electrons from the zinc atoms, and the zinc atoms will go into the solution while the copper atoms will adhere to the surface of the zinc. You did an experiment last year similar with aluminum in place, and you formed copper on the surface of the aluminum. Now this reaction is arising because of an electron transfer, and the electron transfer is actually happening right at the surface of the metal. So what we want to do is we want to make available those electrons that are being transferred and use the electrical energy that's available. In order to do that, we need to set up a galvanic cell. And what a galvanic cell is going to do is it's going to separate the oxidation reaction from the reduction reaction, and it's going to allow the electrons to travel through a wire, and while they're traveling through a wire, we'll be able to make use of the electricity that's generated. So we can measure the voltage, or we could connect a light bulb, or in examples of your laptop or any device that you use that has a battery in it, it's the same principles are being used. We're using a redox reaction and harnessing the electrical energy that's produced in order to make use of it. The Daniell cell is one of the original galvanic cells, and it was set up using this zinc and copper reaction. And like I said, when we want to set up a galvanic cell, what we need to do is we need to separate the oxidation reaction from the reduction reaction. And we do this by creating two cells. So this cell over here consists of an anode, which is a zinc bar in a zinc solution. And we've got a cathode of a copper bar in a copper solution. And we connect the two metals to one another using a wire. Now what happens is the zinc on this side is losing electrons and going into a solution. The electrons are traveling along the wire from the anode to the cathode, and the electrons are being collected at the cathode by the copper ions in solution to produce copper atoms. By separating the oxidation reaction from the reduction reaction and allowing the electrons to travel from one to the other, we are able to harness the electrical energy. So if we've got a light bulb here, we can turn that light bulb on if there's enough voltage produced by this reaction. Now I've used the words anode and cathode. The anode is the electrode where the oxidation takes place, while the cathode is the electrode where the reduction takes place. You can remember which one's which in a few different ways. Anode and oxidation both start with vowels, while reduction and cathode both start with consonants. You can also remember that where oxidation is occurring, the electrons are being produced, so this is negative, as is an anion, while on the other side, where the electrons are being collected, it's going to be positive, which is the cathode. A silly way to remember it, thinking back to Leo the lion says grr, okay, what I do is I think of it as Leo has the hiccups. Instead of saying grr, he says grr, and gain of electrons is reduction at the cathode. Okay, so there's lots of ways that you can remember that, but you need to know that the oxidation is occurring at the anode and reduction is occurring at the cathode. Now, another part of the galvanic cell that's really important is this salt bridge here. Okay, the salt bridge is necessary in order to allow the reaction to continue, and I'll explain why. If we think about this half cell, in this reaction, what's happening are copper ions are gaining electrons to produce copper. As this reaction proceeds, we're actually removing copper ions from the solution. And so if we let it go for an extended period of time, what's going to happen is overall this solution is going to have a negative charge. It's going to lose its electric neutrality. And that is unfavorable for a solution. It does not want to be charged, so if it does end up being charged, the reaction will stop. What the salt bridge does is it provides an inert solution, so a solution that won't react with the other species in the container. And what happens is the ions are able to migrate from the salt bridge into this beaker in order to help maintain electric neutrality. So in this case, because we are taking the positive ions away, the positive ions from the salt bridge will migrate into this solution. When you do this experiment, you'll have experience with the salt bridge, and you'll see that it's a glass tube with a solution in it, and it's got a plug on it that allows for the ions to migrate from one to the other. The same discussion can happen for the anode. Okay? At the anode, the reaction that's happening is the zinc is losing electrons to produce zinc 2+ ions. So as the reaction proceeds, zinc 2+ ions are collecting in this beaker, and so over time this container will actually become more positive. So from the salt bridge, the anions migrate to the anode in order to maintain electric neutrality. You'll see when we do the experiment, if you take the salt bridge out, this light bulb goes off, the reaction ceases. Now we can represent a cell using such a diagram with the beakers and with the anodes and the cathodes, etc. But there's also another notation that we can use that's much simpler, and this is called galvanic cell notation. This notation represents this cell. When you use galvanic cell notation, what you need to do is place the anode on the left-hand side always. So in this case, we've got zinc in a zinc solution. This vertical line represents the separation of the two in terms of their states. So you've got a solid in the solution. This solution is connected to a copper solution that is connected by a salt bridge, which is what this double line represents. And the copper cathode is placed in that copper solution. What's nice about this notation is you can actually see both the anode and cathode reactions that are happening. The zinc is being converted to zinc 2+, and the copper 2+ at the cathode is being converted to copper. Let's look at some examples. In this first example, we're going to sketch and label a galvanic cell that makes use of the following spontaneous reaction. And we're also going to show the cell notation for this cell. One important thing to note about this is that it specifies that it's a spontaneous reaction, and that is one of the features of a galvanic cell. Galvanic cells are spontaneous reactions. Okay, we're going to see cells later on that are non-spontaneous. So these are reactions that are favorable based on the activity series. So the substance that is more likely to gain electrons will, as is denoted from the activity series. So in this reaction here, we've got magnesium going to magnesium 2+, and we've got iron going to iron atoms. So in this case, the magnesium is being oxidized, so it's going to be at the anode, and the iron is being reduced or gaining electrons, and it's going to be at the cathode. To set up the cell, you need a beaker with the appropriate metal. So we've got magnesium bar in a magnesium solution. Connected to an iron bar in an iron solution. It's 2+. Okay, and the anode is connected to the cathode. Okay, we can attach a voltmeter here or a light bulb if we want to. The electrons are traveling, and they always do, from the anode to the cathode. We can show the reaction. So the magnesium here is losing electrons. So that's the reaction that's occurring at the anode, and the reaction that's occurring at the cathode is the reduction of iron ions to Fe. Now we also need to show a salt bridge because this reaction would not occur without a salt bridge. One thing about the salt that you choose for the salt bridge is that you want it to be something that is inert, that will not react with the other substances in either of the beakers. In the example that we looked at before, we used KCl, which is very useful in a lot of cases, but it can be a bit of a problem. So if we were doing a reaction that involved silver, for example, that could precipitate. The chloride and the silver will form a precipitate, and so that's not a good choice for a salt bridge solution. So I like to use potassium nitrate because both potassium and nitrate have very low reactivity, and they are don't form precipitates with anything, so they end up being a good choice. Now, to do the cell notation for this, we need to make sure that the anode is on the left. Okay? For this galvanic cell picture, we could have drawn it the other way. It wouldn't matter as long as we show the correct direction of the electrons. But with cell notation, it is a must that we have the anode on the left, and in this case, we've got a magnesium bar in a magnesium solution connected by a salt bridge to an iron solution which has an iron cathode in it. Now in the previous example we showed the concentrations being 1 mole per liter. That is the standard concentration in a galvanic cell. If you don't show a concentration, the assumption is that the concentration is standard or 1 mole per liter. Okay. You can show the states as well, so we can show that this is a solid, okay, but it's not required. Okay, in question 2, it says to write the anode and cathode half reactions for the galvanic cell. Okay, and we'll also write the overall cell reaction for this. So the nice thing about the way that these are written, like I said before, is that we can see right away what the reactions are. So we know that the reaction on the left is the anode reaction, so we're going to have a loss of electrons, in this case 3 electrons. And then on the right we see the cathode reaction, which is reduction or gain of 2 electrons to form lead. So these are the two half reactions. If we want to show the overall reaction, we need to make sure that the electrons are balanced. So in this case, we'd need to multiply the aluminum reaction by 2 and the lead reaction by 3. And so the overall reaction would be 2Al plus 3Pb2 plus goes to 2Al3 plus 3Pb. Okay, so this is the overall reaction. When you're showing the half reactions, it's appropriate to either show the full reaction balanced with the correct number of electrons, or this would be appropriate as well, just showing the aluminum going to aluminum 3 plus 3 electrons. Okay, now there are some cases where we want to study an oxidation or reduction reaction, but it isn't that of a metal. So for example, we might have the reaction, like in this one here, we've got a reaction where hydrogen is reacting to produce H plus and 2 electrons. Now in this case, H2 or H plus couldn't act as an electrode. So if we want to study an oxidation or reduction reaction that is in solution or involves gases, what we use is what's called an inert electrode. And so platinum or graphite are used as electrodes in those cases. Okay, so they won't interact, but they will allow the oxidation or reduction to occur at their surface. Now, what we're going to do for the rest of the lesson is look at what's called cell voltage. And when we're studying a galvanic cell, we've got electrons flowing from the anode to the cathode. And the reason that electrons flow in that way from the anode to the cathode is because there's a difference in the electrical potential energy between the electrodes. So much like water will fall down a hill, the electrons will travel from a higher potential energy to a lower potential energy at the cathode. And the cell potential is actually the difference between the two. So the final position is the cathode and the initial position is the anode. So if we want to find the cell potential change, what we're going to end up doing is taking the potential at the cathode and we're going to subtract the potential at the anode. So this is going to be a key formula for the remainder of this lesson. Now, the difficulty that we have is that we can't actually determine the cell potential of a half cell. So I can't just measure on its own the potential of zinc to gain or lose electrons. So what we need to do is use what are called standard reduction potentials. Okay. When we do a standard reduction potential, what we are doing is we are comparing everything's ability to gain electrons to a standard. And the standard electrode that we examine is called the She electrode, the standard hydrogen electrode. And what we've done is we've assigned this potential to be 0. And we compare everything else relative to this standard hydrogen electrode. So this is the standard hydrogen electrode here. The reduction reaction that would occur is the H plus gaining electrons to form hydrogen. So this is the example where we would need an inert electrode. So we use a platinum electrode, and what we do is we've got a hydrochloric acid solution and we bubble hydrogen gas through here. Okay, so much like in all the other scenarios, we've got both substances available in the half cell. Okay, so this would be how we look at it as an oxidation, and this is what would occur if it was a reduction reaction. Now we've assigned this to have a potential of 0, and we've used it to create a table of standard reduction potentials. And the way that we've done that is by putting everything relative to this particular cell. Okay? So for example, if I want to know what the relative potential of zinc is, I place it up against the She electrode and I measure the voltage, the cell voltage, which is measuring the difference in potential between these 2 points. Because I've assigned this to be 0, I am then able to determine what the relative potential of the zinc is compared to the She electrode. So when we read the voltage, that's not all the information we need. We actually need to examine the cell to determine what is the anode and what is the cathode of this cell connected to the She electrode. So when we connect the zinc, we read that the overall cell voltage is 0.76. But how we decide which one is the anode and which one is the cathode is by examining the actual substances. And we monitor the mass of the zinc in this case. In this case, the zinc actually decreases in mass. So we know that it is being oxidized, that the zinc electrode is losing electrons to form Zn2+. So I now know that zinc is the anode and the She electrode is the cathode. So these are the reactions that are happening in this galvanic cell with an overall cell potential of 0.76. So as I said before, to determine the E cell, we need to take the reduction potential of the cathode and we need to subtract the reduction potential of the anode. So in this case, I know the overall cell potential is 0.76. I know the cell potential of the cathode is 0 because I've assigned it to be that. So I can find the cell potential of the anode, and it is measured to be 0.76. So if you look ahead in your notes to page 18, you can see the table of standard reduction potentials. If you look at the numbers, you can see it starts with positives, and then there's the 0 point, and that's where the hydrogen reduction reaction is. And if you continue along and see the zinc reduction reaction, you'll see that its reduction potential is minus 0.76 volts. So let's look at another example here. We've got another situation where we've got the She electrode connected to another half cell, in this case the copper reaction. So we've got a copper electrode in a copper solution. The information that we're given is that the mass of the copper is increasing, and it gives us the voltage to be 0.34. So what we need to determine is which one is the anode and which one is the cathode. Because the mass of the copper is increasing, we know that it must be the cathode, because the copper ions are gaining electrons to form copper on the surface of the electrode, and therefore it's increasing. So to draw the cell diagram for this, we know that the anode is the She electrode. We use an inert electrode of platinum. And then we've got H plus and H2, and we're always going to assume standard states unless we are otherwise told. We connect using a salt bridge to the copper solution, and we've got a copper electrode. Okay, so that is the appropriate cell diagram. For the half reactions, okay, we know at the cathode that the copper is gaining electrons, okay, to form copper. And in this case, the She electrode is undergoing oxidation, so the oxidation reaction for that is the hydrogen gas is being oxidized to hydrogen ions. Okay, so these are the two half reactions that are occurring in this cell. To determine the standard reduction potential of copper, we know that E of the cell is equal to the reduction potential at the cathode minus the reduction potential at the anode. Okay, we know the overall cell voltage is 0.34, and we know that the copper is the cathode and that the anode, or the She electrode, has 0 volts. So in this case, the reduction potential at the cathode is 0.34 volts. The last question is to determine the EMF of the Daniell cell. EMF stands for electromotive force, and it's important that you understand that when you're asked for electromotive force, you're simply being asked for the voltage of the cell, or the cell voltage. So if we want the cell voltage, it is the reduction potential of the cathode minus the reduction potential of the anode. And the Daniell cell, recall, is the one involving zinc and copper. And in the reaction with zinc and copper, the cathode is the copper, and the anode is the zinc. So we take the reduction potential at the cathode of 0.34 and we subtract the reduction potential at the anode of 0.76, and in this case we get a voltage of 1.10. Now for galvanic cells, we've said that they are spontaneous reactions. The E cell for a spontaneous reaction is greater than 0, okay, as is the case with the zinc copper reaction. Okay. Now there's just a few things to note about the table of standard reduction potentials. So as we look at the table here, there's a few things. First of all of the reactions are read in the forward direction, and they're all reduction reactions. So in a lot of cases, you'll need to flip the reaction around to determine what the oxidation reaction is. This series is in line with the activity series, and the metals are in the same order on this as they would be on the activity series. So you can see lithium is very likely, it's at the bottom here, so it's very unlikely to gain electrons. Okay, fluorine is at the top of the list here. It's really likely to gain electrons. So the activity series really only showed the metal reactions, but you'll see this is a more complete list and has a variety of other redox reactions of concern, okay, involving gases or solutions like permanganate and nitrates and sulfates, okay, that are useful to us. Okay, so the more positive the reduction potential, the more likely a substance is to be reduced. So the more likely it's going to be an oxidizing agent. And the reverse is true. If you've got a highly negative cell potential, it's going to be very likely to lose electrons instead, and therefore it's a very strong reducing agent. Now, one thing that's important to note is that the stoichiometric coefficients don't affect the cell potential. So when you multiply a reaction by 2 or 3 in order to ensure that the electrons transferred in a reaction are equal, okay, they do not affect the cell potential. It's called an intensive property, so it's kind of like temperature. It doesn't matter the amount of water you have, the boiling point of water is the same. Okay, or density, doesn't matter how much water you have, the density of water is the same throughout. Okay, so those are just some key features of the standard reduction potential chart. Okay. One other thing to note here, if we look at the zinc and the copper, much like the activity series can be used to determine what will happen in a particular reaction. Okay. The one that is higher up on the list is more likely to be reduced, okay, which makes sense based on our discussion of it's more likely to be reduced on the top versus on the bottom. One thing to be careful of is that you want to really look carefully at the charges on the ions to make sure that you're selecting the right one. Okay, so for copper, Cu2 plus 2 electrons going to copper is different from copper just gaining 1 electron to form a copper ion. Okay, so just be mindful of that while you're using the table. Okay, and as noted before, you know that a reaction is spontaneous if the cell potential is greater than 0. So that's a very useful fact, and it will come into play with some of the examples we do here. So in example 1, the standard cell potential of a silver-copper galvanic cell has a value of 0.46. The cell reaction is given with reference to the standard reduction potential of the copper electrode to determine the reduction potential of silver ions. Okay. And it also asks us to use proper cell notation to represent the cell. So in this case, the copper is actually being oxidized, so it's the anode. So you've got copper in a copper solution connected by a salt bridge to a silver solution with a silver electrode. So that's the proper cell notation. We know that E cell is the reduction potential at the cathode minus the reduction potential at the anode. In this case, it tells us that the cell potential is 0.46, and we know that the cathode is silver. So that's our unknown, and we know from our previous example that the anode has a cell potential of 0.34. So this shows us that the cell potential of silver is 0.80 volts. And if you look at the standard reduction potentials, you'll see that that is the case. Number 2, it asks us to predict the reaction that will occur when nickel and iron are added to the solution that contains both nickel and iron ions. So what we have here is 2 potential reduction reactions. So the nickel ions could be reduced or the iron ions could be reduced. And what we want to do is look at the reduction potentials of each of these reactions. For the iron, it's negative 0.44 volts, and for the nickel, it's negative 0.25 volts. And the one that is higher up on the reduction potential list, or has a higher reduction potential, which is the nickel, is going to be reduced. And the other one is going to be oxidized. Okay, so what we have here is the nickel is going to react in this same way. The iron, the reverse reaction is going to happen. So the iron is going to be oxidized. So to write the reaction that's going to occur, we're flipping the first reaction and adding it to the second reaction. And in this case, I don't need to do anything with the electrons. They're already balanced. In question 3, it asks us to use the positions of the half reactions to predict the spontaneous reaction when Br minus, SO4 2 minus, SO2, and Br2 are mixed in acidic solution. So this one is a little bit less straightforward. What you need to do is look at the reduction potentials and find the appropriate reactions that apply to these conditions that are given. So there's one reaction that is SO4 2 minus plus 4H plus 2 electrons going to SO2 plus 2H2O. Okay, and the reduction potential of that reaction is 0.20. The other reaction is of bromine gaining 2 electrons to form Br minus, and the cell potential of that is 1.07. Okay, so I really encourage you to look carefully at the reduction potentials and see how I made the decision to choose those particular reactions. Now, in this case, the bromine is the one with the higher reduction potential, so it's the one that's going to be reduced, and the other one will undergo an oxidation reaction. So much like I did before, I need to reverse the reaction that is actually undergoing oxidation and add it to the reaction that is undergoing reduction. Okay, and so this is the overall reaction that would happen spontaneously in that system. Okay. In example 4, it asks what the cell reaction would be and the standard cell potential of a galvanic cell employing the following reactions. Okay, so again, we're comparing two reactions. The one with the higher cell potential is the one that's going to be reduced. Okay, the one that is with the lower cell potential is the one that's going to be oxidized. So this one is the cathode, okay, and this one is the anode. Okay, so if we want to find the cell potential, I'm going to take the cathode of 0.34 and I'm going to subtract the anode reduction potential of negative 1.66, and I have a cell potential of 2 volts. Now, in order to actually write the overall reaction, I need to be mindful here. I know that the first reaction needs to be flipped because it's the one that's being oxidized, but you can also see that in this case, the electrons that are transferred are not the same, so we need to take that into account as well. And notice that this has nothing to do with the cell potential, so I'm not concerned about multiplying these reactions when I calculate the E cell, but I am concerned when I write out the balanced reaction. So when you multiply them and then recombine them, okay, you're left with 3 copper plus 2 aluminum goes to 2 aluminum plus 3 copper. And as is the same as before, if we look at this reaction, both the atoms and the charges are balanced in this overall reaction. Okay. In this next example, very similar to the previous one, the one with the higher cell potential is going to be the one that's reduced. The one with the lower cell potential is going to be oxidized. So in this case, the overall reaction is nickel oxide plus water goes to nickel hydroxide plus iron hydroxide. In this case, I didn't need to multiply because the electrons are the same in both reactions, but when I flipped the first reaction, the hydroxides ended up canceling each other out. So I really encourage you to take the time to set it up and make sure that you know how to recombine the reactions and get the appropriate overall cell reaction. Okay, the E cell, by taking the cathode and subtracting the anode, we are left with a cell potential of 1.37. In number 6, we're asked to determine whether the following reactions are spontaneous as written, and give a reaction that is spontaneous if needed. So what we have to do here is look at which one is the anode and which one is the cathode, not based on their position on the activity series, but the way that it's written. So in this case, the copper is losing electrons, so the copper is actually the anode. So when you find the cell potential, we're going to take the hydrogen electrode, which is 0, and we're going to subtract the copper reduction potential, which is 0.34. And so in this case, we have a cell potential of negative 0.34. Okay, it's less than 0. So the reaction is not spontaneous. Okay, if you want to write the spontaneous reaction, you write the reverse reaction. So the reaction of copper plus hydrogen going to Cu plus 2H plus is the one that's spontaneous. If the forward reaction is not spontaneous, the reverse is, okay, and that makes sense based on the fact that we're going to switch these around. So the copper would be the cathode minus the anode, and it would simply be positive. Okay, same magnitude, different sign. So in this next one, identifying the actual half reactions is the challenge, but you can see that if you look carefully, that copper in this case is the anode, and the reaction with nitrate and the acid to NO and H2O is the cathode. Okay, and in this case, the E cell is the cathode or the nitrate reaction of 0.96 minus 0.34, which is our copper reduction potential, and we get a voltage of 0.62. Okay, so therefore this particular reaction is spontaneous. And that concludes this lesson.